Hello everyone. Thank you very much, Shihab, for the invitation and introduction. I will talk about optimal investment strategies under the relative performance in jump-diffusion markets. This is a joint work with Morgan Stephenson in the University of Copenhagen. So this is still going on work. I would appreciate for your any comments and questions which will contribute in the direction of the work. You can also interrupt me anytime when I talk. Okay, so first of all, I will give a brief introduction about the problem, and then I will introduce the framework of the models. Also, I will give some numerical results, and then I will conclude the presentation. So the problem is an optimal portfolio management problem. We are trying to determine the optimal investment strategies for a representative agent and a group of people which forms the market. And we are using power utilities. And the agents and the market is interacted with each other with a relative performance concern. So it's actually coming from a classical Merton problem, but here we are working with the relative performances both of the agents and the market, which is formed by a group of people. So this strategic interaction between the agent and the market is caused by their relative performances and therefore their relative values in the portfolio, and therefore we are maximizing their values at the end of the trade session. So therefore we are solving two classical Merton problems to determine first what the market does under these conditions, and then we determine the agent's optimal strategies, where basically we find the optimal proportional allocations of the agent in the portfolio, and this is relative to the market performance. So basically in our setup, the agent doesn't impact the performance of the market, but the market has the impact on the agent. So why we are concerned about relative performance of the agents? Because there are some studies which show the significance of the interaction and the competitive between the agents in the market. And also it's related to the human behavior. There are also some studies that show that the people are competitive to their peers also in the financial markets. And this relative performance concern studies also creates the financial bubbles, which increase the risk of the trade of the agent's wealth. And in our framework, we are working on jump diffusion markets. So the stock price is defined with a jump diffusion process. And here in the numerical solution, we both consider upward and downward jumps. I will show the stock price dynamics and also wealth dynamics. Here is a little literature about this topic. So this paper works on this optimal portfolio choice problem with the competition between two risk-averse portfolio managers, and they follow the geometric Brownian motion. And then this is one of the seminal works in this topic. They considered and they extend this work for interacting agents. And then this paper works on on also this problem under the relative performances for n interacting agents again, but they use both exponential and power utilities. And then they find the optimal equilibrium strategies for both these n agents, and also they find the mean field equilibrium strategies when taking n to the infinity. Then this paper extended this power utility model of this paper for continuous time-dependent problem. And this is also one of the seminal works. Here they use forward utilities, which bring another direction to the area. And lastly, this paper obtained the Nash equilibrium investment strategies, and they also reveal the impact influence of the price impact on the equilibrium. Okay, so how we contribute? Actually, this work is also special case of this paper in the following direction. What we do is actually we simplify the results in this paper. They work with n agents, and then they take the average of all these agents for the Welt process, and then they find the mean field equilibrium. So what we are doing, instead we consider a representative agent in the market, and then we also consider the market, and then they interact each other. But then we see that our results are also obtained. Their results are also obtained from our results. So we also recover their results by our work. Okay, so the price of the stocks is followed in the following jump diffusion markets. We are the agents invest in a risky asset, and they will follow also the jump diffusion process in their Welt processes. I will give more details about that later. And also another direction that we do here is to consider the homogeneous agents case in the market, in their risk aversions and relative performance. So it means that there are indifference between their risk aversions and relative performances. This paper doesn't consider homogeneous agents. They are working with heterogeneous agents. Therefore, their risk aversions and relative performances may be different. Okay, so now I will introduce the framework. So we are working on a classical complete probability space. The aim is to obtain the optimal proportional allocations in the portfolio of the agent and the market. So we denote them by pi and pi hat, respectively. So let X denote the wealth of the representative agent and Y denote the wealth of the market. Therefore, they are generated by the following dynamics. So here, mu and mu hat are the drift constant drifts. So here, P is the common noise, W is the idiosyncratic noise, and we have also the jump processes, and epsilon tilde, and epsilon hat are the jump sizes, and the jumps are generated by the Poisson processes with intensities lambda and lambda tilde. So the aim is, as I said, to obtain the optimal pi and pi hat such that the capital gains are obtained by the following by those dynamics in the risky asset. in a non-risky asset, the capital gains are said to be 0. Okay, so first of all, we write the optimal control problem for the market. First, we use power utility for the market. So we define the utility function of the market is defined by this function. So eta here is the risk aversion of the market. This is actually a classical Merton problem, like I said before. Therefore, we write the optimization problem for the market for pi hat for the following set of admissible strategies here. And then we write the corresponding Hamilton-Jacobi-Bellman equation for that value function.
Can I ask you something?
Yes.
Okay, when you put in the previous slide, the optimal control problem in the previous slide, yeah. Okay, so you put this utility function of the market at the final value, and then you write the optimization problem, right? But
yes,
you
exactly.
put the expected value of V of Y. Shouldn't be Y capital of T capital instead of little y inside of the expectation?
Yeah, but here we that's right, but y is only parameter here. Here, I mean, it only shows the dynamics of this. That is why we write the small y. So we actually didn't.
Can you remind me why what was Y capital? Wasn't it the final the cash that you have at the end, or what?
Y is here. It's the wealth dynamics of the market, and pi hat is the proportional allocation proportion of the market.
Yeah, but Y is in dynamic quantity, right?
Yeah. But here, in general, in the stochastic control problems, since we denote with small letter, that is why we denote. But it could be also denoted by capital Y.
Yeah, but usually, at least in the I'm trying to make sure that I understand the notation. The cost to go here depends on little y and t, right? And the little y usually is the value that enters the conditional expectation for the initial value of the dynamics.
Yes.
Right. Okay. So the value function, the utility function V capital inside of the expectation is evaluated at Y capital of final time, not at little y.
Yes, that's right. Yeah, that's right. Yeah.
Okay, so this is exactly. Is this a typo?
Yeah. Yeah.
Yeah. Okay, this is what confuses me.
Okay. This is conditional. Yes, exactly.
Yeah. Is Y capital of little t equals little y?
Yes.
Right, and the V is evaluated at Y capital of T capital.
Yes.
Yeah. Okay. And then yeah. Okay. Fine. Then I understand it.
Yeah. Thank you. Okay. So then we write the Hamilton-Jacobi-Bellman equation for the value function for the market. Yeah. So this comes from the dynamics of the Y here. So here, this comes from the jump part in the wealth dynamics of Y, and we also add the intensity here. So with this terminal condition. So from here, after we solve this, we obtain this equation. So our aim is to derive pi hat for the market here, but it's a nonlinear. Yes.
Can I still ask you? I'm just trying to follow, right? So I'm looking at equation 3, right? And this equation is just on the state variable y, right?
Yes.
Okay. From the beginning, didn't you postulate a dynamics that had x and y, not just y? Can you remind me
Yes, because this is the market. I will also put the x dynamics for X for the agent. Since this is only for the market, we only we write according to the dynamics of Y.
Okay, so what is interpretation? What is the strategy that acts on the market?
Yeah, I will talk about now actually. I mean, do you ask on önceki ben communication or for the later? Because since this is the
okay, so
this is
I'm just trying to follow. You said that the effect of the agent is not felt in the market, but the market affects the agent, right?
Yes, I will introduce it in a few slides. Yes.
Okay, if that is the case, I just wanted to understand who is controlling the market, because I mean now equation 3 is a control on the market, right?
Yes, nobody now controls the market. Later, I will introduce the optimization problem for the agent, and then their market also will be in the play. I will show it in the if slides, because just the classical market problem for.
Yeah. But I just wanted to understand the pi hat, which is the strategy that is affecting somehow the market, right? This pi hat.
Yeah, exactly. Yes.
I mean, how do we interpret that thing? Who is actually driving the pi hat that affects the market? Because it's not an agent, right? And the agent has no power of the market, like you said.
Actually,
I'm just trying to understand the model, Burcu.
Yeah, the market itself is generating, and it's because market is formed by the agents, and their strategies also determine pi hat here. So the market itself.
So somehow, what you're postulating is that there's some kind of force that optimizes the outcome of the market.
Yes, exactly.
And this force somehow is a coordinated effort of many agents. This is what I'm trying to understand. Who is this force?
Yes. The agents which are formed in the market.
Okay, thank you.
So yeah, it's like there are n agents, for example, in the market. They form this market and they find the pi hat, and then we will write the only one control problem for one representative agent between them. I hope this is clear now.
Yeah, please continue.
Okay, so yeah, so then after here, we obtain the equation for pi hats. As I said, this is nonlinear equation. So we cannot isolate pi hat directly here. But then the special cases come into here. For example, the special cases will be in two cases here. First, it will be the pure diffusion case, and the second, will be the pure jump cases. Okay, now I've introduced the optimal control problem for the agent. So now, for example, in the utility function, we both have X and Y. This was actually what I was trying to tell in a few minutes ago. The theta here is the impact of the market on the agent, and gamma is the risk aversion degree of the agent. So here we can see that the agent doesn't have any impact on market, but the other way around. So we can, on the utility function for the agent, we can see that if theta is 0, which means that the market doesn't impact it, the market's performance doesn't impact the agent's performance. And when theta is equal to 1, then we have this utility function. It means that the market has the full impact on the agent's performance. Okay, now the control problem for the agent can be written as follows. Again, here there will be, of course, the condition. So on this admissible strategies, and then we write the Hamilton-Jacobi-Bellman equation for both using the dynamics of X and Y. So in the supremum, we take the supremum over pi, which is the optimal proportional allocation for the agent on the portfolio. And here, these jumps appear in the dynamics in the wealth of the X. Therefore, we write them accordingly, and we use this final condition here. So after
Burcu,
yes.
Sorry for bothering you, but what about the boundary conditions? Not just the final condition. What about the boundary? Can you make comments on the boundary conditions for this problem?
We actually didn't think about the boundary condition. I think the final condition should be enough because
Why?
it's not, because we don't solve this problem numerically.
Yeah, but even if you don't solve it numerically, right, you have to make sure that the Hamilton-Jacobi-Bellman is a well-posed PDE.
Yeah.
So.
But we were, we didn't think about boundary condition here.
But it's important, right?
Yes.
I mean, you need to ensure that this has a unique solution and things are fine. I mean, if you look at the original dynamics, can you look for a second at the original dynamics?
For X, right?
X and Y. Okay, so jumps here, I mean, are driven by this Poisson process, right? So the dn is always, I mean, the n process is monotonic, right?
Yes.
Okay, epsilon hat, is it positive or not?
They are positive, but they can be also negative, and in depending on the upward and downward jump cases. For example,
okay. But the way you write it, everything is relative, right? So you expect that y does not change sign. Y capital is a process that does not change sign, right? It's always positive. Y0 is positive, and then it stays positive. Okay, so this means that you have a boundary at y capital equals 0. Okay.
Yeah.
So you have to do something about it. And if you look at the x, I think the same happens. X has a natural boundary at 0. So you also have a boundary at x equals 0. Right?
Yeah.
So you need to address this issue in the value function.
Okay, thank you.
Okay.
Okay.
Good.
Thank you.
You're welcome.
Okay. Okay, so we impose the following answers to solve the Hamilton-Jacobi-Bellman equation from the final condition. And then when we insert and when we take derivatives, we obtain this following ODE, where rho tilde is defined by this equation here. And then from there, we obtain this equation 8. This is also linear. So what we want to do is to isolate pi, but it's also not easy to isolate pi. First of all, we have pi heads in here, and also they are in different powers. Therefore, we cannot isolate pi from here directly. But then here, spatial cases again, we are exploring the spatial cases, which will become under the pure diffusion market and pure jump cases. I will introduce them also later. Okay, first, then I show you the optimal strategies for the market. This was the resulting equation for the market. For isolating pi heads, we first impose epsilon head is equal to 0. Therefore, we obtain a pure diffusion market. And then this result is the classical Merton optimal strategy. And when sigma hat is 0 here, then we obtain the optimized strategy for the pure jump cases here as here. So now we introduced the optimized strategies for the agent. So this was the resulting equation. First, we are looking for the pure diffusion model where epsilon and epsilon tilde is 0. So therefore, these two terms will be disappear here, and therefore we will have only pure diffusion model. And from there, we can isolate pi, as in here. And gamma is the risk aversion degree, and so that 1 over gamma is the risk tolerance parameter for the agent. Later I will show the relationship of these results, which were also found by this paper, where they obtain a mean field equilibrium strategy for n agents. So we can also recover their results actually. So this lemma is about that result. So if the agent has the optimized strategy pi, which was given by the pure diffusion case, we can recover the mean field equilibrium strategy in this paper. So first of all, here we show what is the formula mean field equilibrium strategy formula in the paper. It's given by here, and these phi and psi constants are defined by these expectations over each individual, and delta is actually 1 over gamma in our case. They define it as gamma. So if we develop the mean field version of sigma hat pi hat, because this appears in our formula, and then first of all we need to develop the mean field version of this, and then we multiply both sides of the equation for pure diffusion case by sigma, and then we separate it, and then we obtain the formula 13. And now we take the expectation of both sides over all individuals. Which means that we take the average over all individuals. So by this expectation, the left-hand side, the left-hand side becomes the expectation of sigma times pi star, and then the right-hand side becomes this guy, and then these constants phi and psi are denoted by this expectation, and then we equate these two. We found this relation, and then we inserted this relation into our formula, and then it exactly gives us the mean field equilibrium strategy in their paper. So this way we can recover also their solutions for n agents. So when we take n as infinity in their solutions, we obtain our solution. So now we consider single stroke case. In single stroke case, it means that the drift parameters and the volatility parameters are equal to each other, both in the world of agent and the market. And then the idiosyncratic noise parameter is 0. It is specific to each stroke, therefore we take it as 0. So by these conditions, we obtain single stroke case here. And then under these conditions, we can find the optimized strategy as in the formula 15 here. So the proof of this is quite simple. So we just insert these into our formula for pure diffusion case, and therefore we obtain this formula here. And then since we have pi hat and pi here, we take the expectation of both sides. And then if we take expectation of both sides, then we obtain this relation so that the left-hand side also becomes, it's also equal to pi hat. And therefore, we can isolate pi hat as in this relation. And if we plug this into the previous solution, then we can obtain the optimal strategy for the single stock case. I will show you the results for that now. So these results compare our results with the results in Lacar and Zarifopoulos paper with the given parameters for the single stock case. So what we observe, if we look at, for example, to the right picture, to our results, we show the results for varying theta here, for it's the varying relative performance for the agent, but they take the results for the varying relative performance of the market, so we compare both of them. And of course, theta and 1 over gamma are assumed to be uncorrelated to generate this result here. So here we observe that when theta is zero, which means that the relative performance parameter is zero, so that the market doesn't have any impact on the agent. And then we see that the agent puts more money in the portfolio, so that pi increases linearly in here. So when theta is equal to 1, it means that the market has a full impact, so that the pi is gets independent of the risk aversion degree of the agent. Also, the other is observation here. We see that when gamma is greater than 1, which means that 1 over gamma is less than 1, then pi increases in theta here. But here, for example, on the left-hand side, in their results, we can see that they take, for example, theta as 0.75, and if theta bar is greater than 0.75, then pi increases in the risk aversion degree here. Okay, so this picture shows how the optimal investment strategy changes for different theta values. So we just pick some theta values and see the results of pi with respect to the risk tolerance. So we can see the lines intersect at 1, and pi increases in theta when 1 over gamma is less than 1. Okay, now we consider the homogeneous agent case. Up to here, we were considering heterogeneous agents. So now we consider homogeneous agents, which means that the agents are indifferent in the risk aversions and relative performances. Therefore, expectation of 1 over gamma is simply 1 over gamma, and expectation of theta is equal to theta. By this assumption, our results for the single stock case turns out to be this result. So this picture shows the results for the homogeneous agent cases. We can see that again the same behavior except when theta is equal to 1, and when theta is equal to 1 here, there is an immediate jump around some value of pi, which is around 5. This is actually relevant to what we expect, because when the agent wants to increase her wealth relative to the performance of the others. And also when we pick some values in this picture and we compare it with the previous pictures, we get the same pi values, which is also consistent as what we expect. Okay, so this corollary is a result about the behavior of the agent depending on the different theta values. So when the agents are homogeneous in their preferences, the agent's behavior is different depending on the boundary values of theta. So when theta is 0, we have seen that pi is only gets this value, and only here gamma appears, and also this result is similar to the result of the market for the pure diffusion case. And when market has a full impact on the agent, which is theta is equal to 1, the optimal pi is only equal to mu over sigma square, which is only the classical Merton solution. Okay, now we explore the other results, pure jump process. So we obtain this pure jump process with drift when sigma and nu is equal to 0. But under this result, we also have some special cases, which I will also show here. Therefore, with this assumption, we isolate pi from the resulting equation. So we should have, as I said, some more special cases. The first case is when epsilon tilde is 0. Therefore, the equation reduces to this equation. So from here, we can isolate pi, but before that, we take again the expectation of both sides, because theta and gamma appears in the power. So to be able to take the expectation of both sides, first we need to make the homogeneous agents case again, and then we take the expectation, and then pi hat also equals to pi, and then we isolate pi as given in this relation. Okay, so from that relation, we want to have a more simplified equation here, so that we assume that epsilon hat is equal to epsilon, and then we obtain this relation. So for the numerical solutions, we choose the parameters accordingly, which are similar, which will give the same expected return and same variance of the wealth as we did for the pure diffusion cases. So in that cases, mu over sigma square was equal to 5. Therefore, since mu is equal to 5 is not too realistic, so we choose different values of mu and sigma, but still we won't have mu over sigma square is equal to 5 to be able to make comparison. And also the, as I said, the expected return of the wealth and expected, the variance of the wealth of x should be again the same. Therefore, we obtain these two equations with 3 unknowns to be able to make the numerical solutions. So we choose different lambda values. Here, lambda denotes the number of crashes in the market. So it's the frequency of the crash in the financial market per year. So we choose different lambda values, and then we obtain epsilon, and then we find the mu values. I will show you the results. But here also we have a corollary which shows the different strategies depending on the boundary values of the relative performance parameter. When theta is equal to 0, again, which means that market doesn't have any impact on agent's performance, then we have this relation here. And when theta is equal to 1, then we have this relation. And here, for example, when theta is equal to 1, there is no risk aversion degree parameter at all. And this is also similar to the result what we obtained for the pure diffusion case. There also we had we didn't have the risk aversion parameter. Okay, so this result shows the optimized strategies under pure jump cases for different values of lambda. So for example, lambda is equal to 0.1. It means that there is one crash in 10 years in the markets. So we choose different lambda values here. And when we choose different lambda values here, we can see that the solution, the optimal strategy of the agent approaches to the one in the pure diffusion case. So the pi values here smaller, and the pi values are getting increased here. And then when the number of crashes increase, the optimal strategies converge to the results in pure diffusion case here. And also we observe that when we have larger jumps, the return becomes more asymmetric, as we see here. And so that the agent is afraid of being having asymmetric returns. Therefore, the agent puts less money in the portfolio here. And also it's very non-linear when there are larger jumps, and when the jumps when smaller jumps, it becomes more linear here. So these results, the previous results were the upward jumps. Now we show the results for the downward jumps. So it means that we choose the signs of the epsilon as negative here, and we choose actually different lambda values. Why is that? I will explain it, why we didn't choose the same lambda values here, because arbitrage occurs in this case. So first of all, the first observation is that when lambda gets larger, as we can see, again, pi values converges to the pure diffusion case. But here, pi value starts from larger values here, as the opposite to the downward jump cases. And next, we see that when we take lambda as 0.1, as in the previous results, we obtained, the model produced negative epsilon and positive mu values. And this was actually resulting in no solution of the problem. And then we see that for lambda values up to 1, the model results no solution. And when lambda is equal to 1, we find that the return is 0 under the zero rate assumption. And this means an opportunity to win when there are stocks. So it's actually an arbitrage opportunity, because when lambda is equal to 0.1, there is no solution. And when lambda is equal to 1, then we obtain 0 return. So it means that between the jumps, so the investor can earn the same money in the bank as she can do in the stocks, which is namely 0. So that means that if there are stock, agent wants to participate in a game where she can only gain. So when there are upward jumps and when lambda is equal to 1, there is opportunity to win when there are the stocks, because here the arbitrage opportunity is to borrow the money from the bank and then buy the and then buy the stocks, and this portfolio costs 0 to construct. And when lambda gets larger, which means that the jumps are upwards, then it means that the return gets more positive, so that the investor, the agent can return more than 0. So this is resulting in arbitrage opportunity. It's even better for larger jumps, because then the agent can earn more money. Yeah, so as we can see, when lambda is less than or equal to 1, we have arbitrage, and the portfolio optimization has no solution, and therefore we choose these lambda values here, and we see that again, when lambda gets larger, the results approaches to the result in pure diffusion case. Okay, so in this, under this case, the other situation is when epsilon is 0. In this case, then the resulting equation returns to this equation. Therefore, we obtain optimized strategy, but here we see that there's no relative performance here. Therefore, we don't show the numerical solution, since there's no relative performance, so that we cannot make a comparison here. But there is a result here when sigma is 0 and epsilon is 0. We have, which means that this case, we have jump diffusion case, but we don't have any joint risk between the agent and market, and therefore theta doesn't matter at all. So it disappears in the optimal strategy. So the only the theta appears only when there is joint risk between the agent and the market, which is the sigma tilde and epsilon tilde are positive values. The other case is when epsilon is equal to epsilon tilde, and then the resulting equation reduces to this equation. So again, in order to, this is still nonlinear to isolate pi, so that we make some assumptions here, so that we suppose that epsilon is equal to epsilon hat and lambda is equal to lambda tilde. And then we take the expectation, but again, in order to take expectation, we have the homogeneous agents assumption, and so that we obtain this equation here. But here again, 1 minus pi epsilon has different powers, so we cannot isolate pi here. But we have the following corollary: when theta is 0 in this equation, we can find the optimized strategy pi as in given this relation. Again, there is no relative performance here, except value 0 of theta, we cannot isolate pi from the equation 21. So the other result is that when theta is equal to 0, which means that there is no relative performance between the agent and the market, gamma, which is the risk aversion degree of the agent, it always appears on the optimized strategies. But when theta is equal to 1, the risk aversion degree doesn't appear on the formula, because it doesn't matter at all, because all agents have the same, has the full impact by the market, so the risk aversion degree doesn't matter at all in this case. So we also have looked at some benchmark portfolios here under only this case. First, we look at small benchmark portfolio. For this, we insert the optimal strategy of the market that we obtained from the optimal control problem for the market. We insert that formula into the formula for the agent for the agent as instead of pi hat here. So we just insert this result here. And then we want to find more simplified and more meaningful equation here. Therefore, we again make the assumption of homogeneous agents case. So it's this case actually. And then we obtain optimal pi with relative performance and also the risk aversion degree of market here. So other benchmark portfolio is a market benchmark. It's which means that market is clear, so that we just plug pi hat is equal to 1 into our formula. Therefore, we obtain this formula. We still have the relative performance parameter here. And then we make the comparison between these benchmark portfolios also, which you can see here. So again, we found the parameters such that we have the same expected return and same variance. So this left figure is for the small benchmark portfolio, and the right figure is for the market benchmark portfolio. So we can see, for example, in the right hand figure, when there is no relative performance, in both figure, actually, when there is no relative performance, pi increasing in risk tolerance of the agent here. Okay, so this was the last result that I wanted to show. So the conclusion is that we considered optimal portfolio strategies under the power utility function in a jump diffusion market and under also relative performance concerns between agent and the market. So we obtained the results for the agent. So we also, by these analyses, we simplified the models in the reference paper. Also, we obtained their results, and then we found that the influence of the market for different influence values changed the decision of the agent with a combination of the risk aversion degree of the agent. And also we saw that the number of crashes in the market in the jump cases affect the agent's decision, and also it even creates the arbitrage in the market. So this was the end of my talk. These are the some bibliography and references that I use. Thank you very much for listening. If you have questions.